Hello and good morning, everybody, and thank you for joining us for our Ansys Virtual Academy, where we run a bi-weekly webinar on the Ansys products. And for today's topic, it's going to be on the basics of heat transfer modeling uses Ansys Fluent. This is going to be a part 2 of a short series. And as analysis simulations analysts, you might be familiar with doing heat transfer with the Ansys tools. But one of the limitations is some conjugative heat transfer capabilities that your convection coefficient. I really do appreciate the CFD solver and what it's able to do there for us as an analyst. And I feel like the Fluent program is great for bridging that gap between the structures and in terms of heat transfer. My name is John Dow. I'm your host for today. And I'm going to introduce you to my colleague, Snehda Sakar. She's going to be running this webinar for us. She's our CFD specialist, and she's going to be giving everyone a demonstration today on part 2 for Ansys Fluent heat transfer. Please take it away, Snehda.
Thank you so much, JD. Hi, everyone. Good morning. My name is Snehda Sarkar. I'm the CFD application engineer here at KETIV Technologies. Very excited to have all of you with us here today. As JD mentioned, today's session is going to be a deeper dive into the heat transfer modeling capabilities that Ansys Fluent has to offer. And even though this is a part 2 of the previous session, wherein I'm going to be building on some key thermal modeling concepts, you will be able to follow along even if you haven't gotten a chance to go through the previous AVA session. For reference sakes, you can always visit our YouTube KETIV page, and the previous video is uploaded over there. So if you think that there's any merit to going through the content, please feel free to do so. This is going to be a more relaxed, laid-back session. It is going to be more demo-oriented. So I'm going to be covering a lot of concepts during the demonstration. If at any point I miss mentioning something, or you have any questions, please feel free to put them in the Q&A box on your screens, and I can take those questions either during a case loading or towards the end of the session when I find time. All right, so without further delay, let's jump right in. So for today's session, we're going to be covering some concepts that I didn't get the chance to cover in my last AVA, and I think these are some really cool capabilities that Ansys Fluent has to offer, and anybody who's dipping their toes in the thermal modeling pool might want to be familiar with these capabilities. So first of all, we're going to be talking about multi-layer shell conduction. That is a feature that is available with Ansys Fluent, which allows you to shorten your computation and pre-processing time by a lot. The other thing that we're going to be covering is a forced convection problem. We're going to be demonstrating how to set up a problem wherein the fluid has certain velocity, and how such a problem can give you more accurate heat transfer coefficients, something that JD was talking about earlier. We're also going to be learning how to set up interfaces for non-conformal meshes within Ansys Fluent. If you have a combination of different types of mesh wherein the node points are not coincident, how do you map heat and flow fluxes from one domain to another? That is something that I'm going to be covering in the demonstration as well. And in the end, we're going to be post-processing some common heat transfer quantities that people usually are interested in. During the demonstration, I will be covering some tips and tricks that might come in handy when you're setting up something similar. So this is a slide from my last presentation. Just want to quickly recap what we went over on the conduction side. I talked about the basic modes of heat transfer and started with conduction. wherein we know that the heat transfer takes place from a particle of higher kinetic energy to a particle of lower kinetic energy, usually in solids because they're so closely packed together. And you have your heat transfer in that particular fashion. We talked a little bit about thermal conductivity, this value over here called K. This is one of the material properties that you specify. And this thermal conductivity makes a big difference when you're calculating heat transfer quantities. Oftentimes, the accuracy of your solution also depends on the material properties that you choose. And we talked about 1D heat transfer as depicted in the image at the bottom, wherein your heat transfer is only occurring in the normal direction to your face. And we covered something called, thin walls in the previous AVA lecture. So if you want to go and take a look at that, you might find it useful for your study. But in this particular AVA, we're going to be talking about multi-layer shell conduction that lets you model heat transfer not only in the normal direction, but also in the planar direction. So what is multi-layer shell conduction? Whenever you want to model heat transfer through solids, there are two ways of going about it. Either, you model the mesh accurately, wherein you're physically including all the layers of different materials with different thermal conductivities, and that increases your domain, that increases the number of cells for computation, and that also increases your time and effort while building the mesh in the pre-processing stage. The other way of modeling, multi-layers in your physical domain is to use this capability called the multi-layer shell conduction. What this basically allows you to do is if you have a wall with 0 thickness, you can virtually add different layers of material over that wall without actually having to model those layers. So for example, you have a pipe that has an aluminum wall, but it also has a copper layer on top of that aluminum. Say the thickness of that copper layer is around 5 millimeters. Now, instead of actually modeling those 5 millimeters in your mesh, what Fluent allows you to do is just specify the thickness within the GUI, and then Fluent will build the mesh behind the scenes to give you approximate values of heat transfer through that additional layer. You don't have to limit yourself to any one material. You can choose different materials for different layers. So instead of having just one copper layer, you could have additional layer of, say, grease. You could even include a layer of air. It doesn't necessarily have to be a solid. As long as the material properties are defined correctly in your GUI, you should be able to model that thermal conductivity into your problem to get accurate solutions for your heat transfer throughout the layers. When I'm going to be demonstrating the case that I set up today, I'm going to come back to this slide and talk about these images at the bottom. And the reason for doing that is to make sure that you as users can understand how to post-process quantities from a multi-layer shell conduction problem. The other concept that I'm going to be covering today is forced convection. We talked about convection a little bit in our previous AVA, wherein I demonstrated a natural convection problem wherein you have convection currents because of buoyancy effects. Forced convection is a little bit different. I haven't demonstrated anything under forced convection yet. Usually, most of the problems that we see in the industry somehow relate to forced convection, wherein you have a fan or a pump that propels the fluid with a certain velocity. We know, from Newton's law of cooling that the usual heat transfer quantity that we're interested in is the heat transfer coefficient that you see in this equation. As JD mentioned earlier, while introducing today's session, usually we make guesses for this average heat transfer coefficient. There are some, established experimental results based on which, if you look at the table over here, depending on whether it is a natural convection case or a forced convection case, depending on the fluid at play, you have certain ranges within which you can predict the value of this quantity H. However, this is not the best practice for estimating this heat transfer coefficient because it is highly dependent on the fluid flow velocity, especially in cases where turbulence comes into the picture. And as we know in the industry, most of the flows are turbulent in nature. So depending on which turbulence model you choose in Fluent, how you resolve your boundary layers, whether they are being resolved correctly, this H value can be highly sensitive to these additional variables. So the best practice is to actually model the fluid flow over the body instead of just assigning a heat transfer coefficient to estimate the heat transfer overall. And this is something that we demonstrated last time, wherein by just assigning a standard uniform heat transfer coefficient, we were not able to get accurate values. But when we actually built a fluid domain around a body, we were able to see the variation in heat transfer coefficient depending on the location of the solid surfaces and what sort of velocities were in the vicinity of that body. So this is something similar to what we're going to be doing today. And when I do the demonstration, I'll talk about this a little bit more. Now, if you are getting started with thermal simulations or interested in thermal simulations, what is the point of studying conjugate heat transfer or even trying to do this within CFD? You might be looking at thermal management, and that is a common application that we see in the industry. Usually, you do not want your sensitive materials to go beyond the temperature limit. You might want to look at the heat flux rates and the heat transfer coefficient to make sure that you've selected the correct material, that your geometry is designed correctly. If you need to change the design based on your heat transfer prediction or your temperature prediction, then CFD lets you do that, right? For example, I have worked in the automotive industry, and I know how important it was for me to identify the heat spots and make sure that there is no failure mode in the engine environment. The other thing is that you could always use your heat transfer coefficient results from Fluent to couple it with structures analysis on the FEA side to understand what are the effects of this heat transfer on the overall structure. That is something that we will be covering in a future AVA session. So if you want to see this sort of an example wherein we do a coupled analysis between, say Ansys Mechanical and Ansys Fluent, make sure, you enter that in the feedback section at the end of the AVA, and that'll help us prioritize that topic. The other thing that I'm going to cover in today's session is the creation of interfaces. And I have included this topic because there were a lot of questions in the previous AVA on how to make sure that, we have interfaces in a model wherein we have a non-conformal mesh. Now, what do I mean by a non-conformal mesh? Oftentimes, we'll use different types of cells, or perhaps will mesh different domains separately. Now, when these domains are combined together, it's not necessary that the node points at the boundary are coincident. For example, if you look at the image on the screen, the blue mesh and the green mesh at the intersection are not exactly coincident. When the node points are not talking to each other, how do you transfer quantities from one side of the mesh to another, right? This is what you would call a non-conformal mesh, wherein the boundaries are not talking to each other. In that scenario, Fluent has the option of creating something called an interface. An interface is basically created at the junction of these two non-conformal meshes. And what it basically does is it passes the flux from one mesh to another. That could be a flow flux, that could be a thermal flux. It basically interpolates and transfers the quantities from one side to another. For our heat transfer example, we want to make sure that our interface is coupled, which means that whatever heat transfer we see on the solid side passes on to an adjacent solid side or an adjacent fluid side. Or if there are two fluid domains, then there is both thermal and flow flux transferring from one side of the mesh to another. When I talk about the demonstration, this example will be a little bit more clear. And I'll also talk about the additional capabilities that you have, that you have within Fluent to make this task easier. Now let us jump into the demo. And before I switch to Fluent, let me briefly give you a problem statement for the example that I will be covering. What you see on your screen here is basically a louvered fin heat exchanger. You can see that there's a stack and we have multiple fins, and you also have copper tubes in between. Now there is a fluid that's flowing inside these copper tubes that we will not be modeling for the sake of simplicity. But what we will be modeling is the flow of air over these fins. So air will be entering from one direction and blowing over these heat exchanger fins, and will take away some of the heat that is coming from the fluid inside these copper tubes. Now, in order to make this a little bit more efficient and reduce the computational domain, we're not going to be modeling all the fins or the entire section. We'll just be modeling the section that you see in between these two yellow lines. And we can do that with the help of symmetry boundary condition and a periodic boundary condition. What we're basically doing is we're going to model the flow over just one pass of this heat exchanger. And we're going to be assigning periodic boundaries at the top and at the bottom. And we're going to be assigning symmetry boundary conditions on the side. When I switch over to Fluent, I'll talk a little bit more about that. The other thing that I wanted to demonstrate is the use of multi-layer shell conduction. So even though the original problem just had copper tubes through which there was a fluid flowing with a certain temperature, I'm also going to add an additional layer of aluminum over these copper tubes, say 2 millimeter thickness, and we're going to see how to post-process that multi-layer shell conduction problem after we solve it. All right, so let's jump to Fluent. And the first thing that I'm going to do is I'm going to read the mesh of the problem that we're going to set up. I'm using Fluent 2020 R2 in case anybody had a question about that. And while we're waiting for that to load, I see there's a question here. Could this shell method be used to model, say, a porous region where you might not want to make a really fine mesh to model multiple layers through a very thin region? Are you talking about modeling a porous jump? Because if you knew the pressure drop for a particular velocity through that particular layer, you could just go ahead and do that. And if you wanted to include the layer for the sake of heat transfer, then there's a way in Fluent for including the heat transfer in a porous region. There is a thermal equilibrium method, and then there is a non-thermal equilibrium method. So we could do that. But shell conduction doesn't really account for porosity. If you had the equivalent thermal conductivity for that layer, perhaps that would work. But when I actually show you the setting up of shell conduction, you'll see what inputs we can define within Fluent. So I hope that answers your question. And if you had additional questions about how to set up heat transfer in porous region, please feel free to reach out. I'll include my contact information in the end, and I'll be happy to answer that question at that time. So here we have the mesh of the problem that I just described. And you can see in the Fluent GUI, it's very clear, very easily understandable how the fluid is entering and leaving the domain. Like I said, we're not modeling the entire length and breadth of the heat exchanger. We're focusing on a certain section. And because this is symmetric, we can do that. We can reduce a computational domain into smaller section if we can perhaps use symmetry boundary condition. Let me go ahead and do one thing. Since I want to talk about non-conformal meshes, I'll go to display and I'll turn on edges. Right now you can only see faces. So let me go ahead and do that. So now you can see the mesh as well. What you will notice is we have created a fluid domain around the solid body. And in this fluid domain, we have an inlet on this side from where air is entering at a certain velocity. And then at the end over here, we have a pressure outlet where we're specifying 0 gauge pressure. At the top and the bottom, we have a periodic boundary condition. And we can use a periodic boundary condition because these boundaries are repetitive in nature. If I switch over to this picture right here, you can see that these are stacked, right? So these are repetitive in nature. Whatever is going in from one periodic boundary comes out of the corresponding point on the opposite boundary. And these boundaries are situated halfway between two successive plates. So that is at the top and very bottom. And then on the sides over here, we have used the symmetry boundary condition. Whatever you see in.
Sorry to interrupt. I think we can only see your PowerPoint, and then we can see your other screen.
Hey, yeah, Snigdha, I thought my screen was frozen. I think you have just been sharing the PowerPoint this whole time.
Huh. That is weird. Can you see my Fluent right now?
Yes, we could see it now.
Okay. Thank you, Vihan, for pointing that out. So you were not able to see any of the Fluent window?
No,
earlier?
I think the PowerPoint. Yeah, I think the PowerPoint was being shared.
Okay. Sorry about that. Apologize. I'll start from the very beginning of reading in the mesh. So basically what I did was I read in the mesh for this particular geometry. And like I was saying earlier, we are reducing the computational domain so that we don't have to account for the entire length and breadth of the heat exchanger. We are concentrating on a simple section. And the reason we can do that is because the geometry is symmetric and periodic. When I say periodic, what do I mean? I mean that if you look at the geometry over here, there are stacks of the heat exchanger fins. So instead of modeling airflow and heat transfer for each of these plates, I'm just taking one plate into account, right? And what I do is I use the periodic boundary condition to cap off this fluid domain at the top and at the bottom. So whatever you see in blue is a periodic boundary condition. What that basically means is that it's repetitive in nature. So whatever is going in through one periodic boundary comes out of the opposite side of the periodic boundary on the other side, right? The other thing that we're doing on the sides is use a symmetry boundary condition. What is a symmetry boundary condition? A condition through which there are no fluxes. So there is nothing going in or out. And we can do that because along a symmetry face, you can just create a mirror image of the domain that you're simulating. So about this space, I can just repeat the breadth of this geometry. It acts like a mirror face, right? So nothing is coming in, nothing is going out. On the left here, you have the inlet through which air is going in at a certain velocity. And here at the right, This red boundary depicts the outlet at which we're specifying zero gauge pressure, right? Now let us look at the mesh. So I turned on the edges while displaying the mesh. And what you notice here is that most of the domain has hexahedral cells, right? But then where we have the fins and the louvers, we're using polyhedral cells to better conform to the geometry and also make sure that, we are able to capture this correctly. However, one thing to note is that where these hex cells meet these polyhedral cells, if I zoom in, you'll notice that the nodes are not coincident. That means this mesh over here is not really talking to this mesh over here, which basically means that I have a non-conformal mesh. And before I set up anything, especially for a conjugate heat transfer problem, I need to make sure that I create an interface so that heat transfer quantities from one domain can pass on to the other domain. So let me show you a little bit more clearly. If I go to a fluid domain and turn this on, so what I'm going to go ahead and do is switch, click on display. So at these boundaries, you can see very clearly that on one side you have poly cells and on one side you have hex cells, and they're not really talking to each other. Let me look at the questions. There are a lot of questions. There are a lot of comments about not being able to see Fluent. I apologize. And sorry, I thought I was sharing the entire screen. Sorry about that. So yeah, we can see that, there's a non-conformal mesh over here. So let's go and make the interface. How do I go ahead and do that? I can basically go to domain I can basically go to mesh interfaces, and Fluent gives you an opportunity to select something called the auto create. And what that does is it automatically identifies all the boundaries wherein you have to create an interface and automatically creates this for you. I think this feature was introduced after Fluent version 18. This is something really cool that takes care of setting up the model correctly for you without you having to go through all these surfaces. Because this seems like a simple enough geometry, but if you're working with complex geometries that have a lot of faces, the mesh is being assembled from different locations, then you might not keep track of the surfaces that need to become interfaces. So in that situation, using this auto create option will make your life much simpler. You could also select manual create if you know which faces lie on either side of that interface. So for example, if I click on manual create over here, it gives you the option to manually select a surface on side 1 and then specify the adjacent side for that particular surface on side 2. So you could do this manually, but for all intents and purposes, Fluent does that job for you, and you don't really have to go through this exercise for this problem. So I'll go ahead and close this, and I'll auto create everything over here. And so you can see these zones being created in the console down below. And the moment these get created, the mesh interfaces side gets populated, so you know that these interfaces have been created. So I'll go ahead and close this. And every time you manually or create interfaces within Fluent, it's a good practice to just go ahead and check the mesh in case any negative volumes have been created. So I'll go ahead and click check. and I don't get any warnings or red flags, so everything looks good. Now, one thing I do want to point out is that in this particular case, the mesh that we imported was non-conformal. However, if you're building everything from scratch, or if you're using options like share topology within SpaceClim, then when you import the mesh inside Fluent, chances are that it will automatically be conformal. So you wouldn't need to create an interface in that situation. Interface will only be created if you're using non-conformal mesh, for example, for conjugate heat transfer, or if you're using sliding mesh and you're doing the pre-processing and design modeler, then you'll choose these sides on either side of that interface. But if you're building the mesh from scratch, for example, if you make sure that all your mesh is coincident at the boundaries, then you don't need an interface to do conjugate heat transfer. Then your walls will be automatically coupled, right? So let's go ahead and set up this problem. We have set up the mesh properly. We'll go ahead and change the units to Celsius from Kelvin. Okay. And then we'll go to models. By default, the SST K omega model is usually selected, but we're gonna change this to laminar in this case, since I'm selecting a very low velocity and I've already done the calculation to know the Reynolds number. So this is a laminar flow, not turbulent. Let us turn on the energy of force for doing conjugate heat transfer. Anytime you're doing any sort of thermal simulation, anytime temperature comes into the picture, energy needs to be turned on. We're not doing radiation as such in this problem, but if you wanted to turn on radiation, you would simply click on it and choose the appropriate model. So for this case, let's just go ahead and cancel it. None of the other models apply, so we can forget about this section. And we move on to the next one, which is materials. Now, by default, air and aluminum are usually present in your domain. So we don't need to do much because the fluid that is entering at the inlet is air. And apart from the tubes, most of the fins are aluminum. But the tubes, if you remember, were made of copper, right? So I'm gonna go ahead and create another material for copper. So I'll choose from the Fluent database. The material type is already solid. And I will choose this material copper. And once I do that, whatever properties are applicable to this problem automatically get chosen. If there are other applications for which you're using copper, then other properties may get populated. One other thing that is very important to people who are doing thermal analysis is that oftentimes these properties are not really constant. They may vary with temperature, right? For example, conductivity might change with temperature. If you want to do an accurate simulation, then you have the option of choosing, say, a polynomial, right? And the moment you choose polynomial, you have the option of entering the number of coefficients, right? And in this case, if you enter your coefficients, you should be able to plot a chart between your conductivity and your temperature. And if you have a chart on your end, say in an experimental paper that shows how the conductivity varies with temperature, then this just acts as a gut check between what you see in Fluent and what you see in your paper, and that will help you assign the correct values. For some reason, it's giving me a red flag over here, but doesn't matter because I'm just going to be using a constant value for this particular case. But this is a really cool feature that is present in this latest version of Fluent that you can definitely use to your advantage. So I'm just going to go ahead and add copper as another material along with aluminum, and let's go ahead and define it. For all the fluid zones, since air is the only material, I can assume that they have been assigned correctly. For the solid materials, however, we need to be careful. The heat exchanger is, for the most part, aluminum, but the tubes are copper, right? So I have named the tubes as tube 1 and tube 2. So let me click on it. And you can see by default, it has been assigned as aluminum. Let me go ahead and change it to copper. Go ahead and do apply. And it does so. I'm going to go ahead and copy this cell zone condition to the other tube as well. So I'll right click on it, click on copy, and copy it to solid tube 2. Once I do that, let's just click on solid tube 2 to make sure that the right material has been selected. And you can do this manually. I'm just showing you some tips and tricks in case you're not so familiar with the Fluent GUI. And there are these really cool things that you can do now. And yeah, just thought it'd be a good idea to highlight those features. So now that we have assigned the materials to the cell zones correctly, let us come to boundary conditions, right? And what I'll also go ahead and do is I'll go to display and turn off the edges so that we only see the faces, and that way it'll be a little bit more clear as to how we're assigning our boundaries. If I just wanted to highlight the walls, then let me go ahead and do that. So you can see all the walls in your domain. Right now it is colored by type, which means all the walls share the same color. I can go ahead and change it to color by ID. And what that will do is display all the colors based on the name of the boundary condition. So if you assign different name to this part, then it's going to be colored with a different color, right? So let's start with the inlet. It has automatically been called a velocity inlet. So let's click on it and assign a velocity of 4 meters per second. So this is for the air that's coming into the domain. And for the temperature, let's just assign 20 degrees Celsius. Right. Another cool feature that is now available is you can directly just click on the GUI, and that'll pop up this quick edit window wherein you can do some editing of the boundary conditions on a high level. So you don't really have to access the outline view all the time. You can simply just click on any wall or any other boundary and assign the boundary conditions over here. If you wanted to access, all the features that are available to you in the boundary condition GUI, then just go ahead and click on more, and that'll open up the actual dialog box. So there are no conditions that need to be specified on the interface or on the internal walls. Let's look at the outlet boundary condition. So this is 0 gauge pressure, nothing more to do over here. And let's assign a backflow temperature of 20 degrees Celsius. So if there is any reverse flow, we are specifying that that temperature be 20 degrees Celsius. Okay. And now let's come to the walls. The periodic and symmetry boundary conditions don't really need any treatment because, like I said, for the symmetry boundary condition, there are no fluxes that are going in or out. And also for the periodic boundary condition, it's, I don't want to go into the details of periodic boundary condition, but for this problem, we don't need to specify anything. So let's click on walls. So for all the walls that we see, we don't really have to do anything for the aluminum walls, but for the copper walls, I am going to assign multi-layer shell conduction and also a convection boundary condition. Why convection boundary condition? Because there's a fluid that's flowing inside these tubes that we're not actually modeling in Fluent. So I think it's a mixture of ethylene glycol with some other fluid, and we know the approximate heat transfer coefficient values. So instead of actually modeling the fluid, we're just going to assign that convection boundary condition on the wall. The other thing that I wanted to show was how to build a layer of a different material on this inner tube. And that's something that I'm going to be showcasing right now. So if you only wanted to look at the boundaries that start with wall, just go ahead and put wall in this filter section, and that makes it easier for you to skim through all the zones. And let us click on the inner tube because that is the boundary that you see over here. So if you wanted to double check, you could just simply display these two. So you can see that this is the wall that's on the outer end facing the fluid domain, which hasn't been actually modeled, but we're going to assign a convection boundary condition. So I'm going to click on the first one. And we are going to select convection over here. And we're going to assign a heat transfer coefficient of 1050 watt per meter square Kelvin and a temperature of 80 degrees Celsius. So what I'm basically stating is that ethylene glycol is flowing inside these tubes with an assumed heat transfer coefficient of 1050 watt per meter square Kelvin and a temperature of 80 degrees Celsius. So that would basically be the source of your heat, right? What I also want to do on this inner tube is introduce an additional aluminum layer on it. So this is where I will turn on shell conduction. I'll click on it and then go ahead and edit it. So it says, how many layers do you want? Right now, I just want one layer of aluminum, and I'll specify thickness of 2 millimeters. If I wanted to add these shell conduction layers, I could go ahead and make it 2 or even 3. In certain cases, if you want to model an air gap, instead of selecting copper from the material list, you could just select air and then specify the thickness. This is really advantageous because, you know, these layers can be really thin. And if you were to model this in the pre-processing stage, then your mesh has to be really fine. And that just adds to your overall computational domain and effort. So you don't want to do that. So in this case, I'm just going to go ahead and limit it to 1. I'll hit OK. And I'll go ahead and do apply. And then I'll copy this boundary condition to the second tube and go ahead and hit copy. Just to double check, let's see. So everything has been copied over here, right? And then I'm just gonna, there is nothing else to be done on this front. We're just gonna go ahead and set up some report definitions. These are report definitions that you set up to monitor the convergence of your solution. If these steady out with each successive iteration, then you know your solution is converging, you know, to a point. So let me just go ahead and do pressure at the inlet and outlet. So let me do mass weighted average of pressure at the inlet. And I'll report the plot of this and go ahead and do OK. And let's also do a pressure outlet. We can also go ahead and create an expression out of these. So for example, if I wanted to look at the pressure drop, then I could basically use this pressure in minus pressure out, and that would be another derived expression that you could monitor over time, right? You could also look at the flux or any other value that you wanted to report. For example, you could do an enthalpy flow rate at the outlet. That is also often used to make sure that your energy equation has converged. So oh, I hit compute instead of plot. Anyways, you get the picture. So we can go ahead and do that. And then we're just gonna make sure that our convergence criteria is set accordingly. Right now, let's just keep it as 1e minus 3. You could make it a little bit more tight. You could change it to 1e minus 6, but in the interest of time, let's just skip this part. And in methods, let's just go with the default selection. I'm going to switch on the high order term relaxation for a little bit more robustness. And if I go to initialization, I'll go ahead and do a hybrid initialization. So what this basically lets me do is initialize over the entire domain, and it's going to go ahead and do that for me right now. And I'm not going to actually run this simulation because, you know, the iterations will take time. But what I will do is I will load a case that I've already solved so that I can talk a little bit about the multi-layer shell conduction post-processing. So while that is loading, let me go back to my presentation. So when you create multi-layer shell conduction, or when you assign an additional layer on any wall, where does it get created, right? So whatever layers you add are added between the wall, the original wall, which is represented by B wall in this image, and then the outside domain. So for example, in my case, this would be the tube wall, and this would be ethylene glycol. I've just added one layer. So if this is the extra aluminum layer that I created, right? I think I assigned a thickness of 2 millimeters. Then this surface over here that is adjacent to the virtual fluid will be called B wall colon external. So wherever you see external, that would be the last wall between the virtual fluid or outside and your original domain. So if I go back to Fluent, this takes a little bit of time. I will be able to, you know, post-process this additional wall that is created because of the use of the multi-layer shell conduction capability. It usually is faster than this. So now if I go to results and I look at contours, you will notice that I have all these original walls over here. This was what I set up in my pre-processing stage. But you'll also notice these external walls that have been created because of the use of multi-layer shell conduction. So if I were to look at Sorry, temperature. So you can see that the inner wall, which is adjacent to my solid domain, has a minimum temperature of 39 degrees Celsius. And if I were to look at this external wall, then it's a little bit higher because it's on the exterior, adjacent to the 80 degrees Celsius fluid, which is why the temperature is around 40 degrees Celsius, right? So this is a good gut check to make sure that you're looking at the correct wall quantities when you're looking at post-processing results, right? I'll quickly load a solution case to go over some of the common post-processing quantities because we're running out of time. But if you have any questions, feel free to put that in the Q&A box right now, and I can take that while the file is being loaded. The other thing to keep in mind when you're post-processing convection coefficients is to assign the correct reference values, because if I am looking at heat transfer coefficients, then my bulk temperature and my free stream temperature, they make a huge difference. If you change the reference values, your heat transfer coefficient changes. And my recommendation is, if you're using CFD results to compare with established results from a paper per se, then make sure that your reference value in Fluent is the same as the reference value in your experimental paper. Otherwise, you may find that the results vary, and that will just cause unnecessary doubt. So this is an already solved case with converged solution. And I just quickly wanted to go over some of the quantities that could be of interest for anyone who's doing this sort of a simulation. So you can see over here on the left, you have different sorts of results. If I look at the contour, so initially you basically have a temperature contour on the heat exchanger. Let's just make this smooth. So you can see, based on the direction of airflow, you have cooler air that is coming in from here. And then as it moves over the heat exchanger, it picks up heat, and there's less heat transfer over in this section over here. And these are the temperature contours on the plane, which shows how the temperature is varying as air moves over from one section to another. You can also look at the path lines to see the airflow over these heat exchangers. And even if you're not doing heat transfer simulations for the sake of correlation or design improvement, if you wanted some really cool images to go on your website or just intuitively predict the right values, you could definitely leverage a tool like Ansys Fluent to achieve that. If you wanted to look at heat transfer coefficient, then you could simply choose the area weighted average and then go ahead and select surface heat transfer coefficient for all the fins over here. So the fins are already selected. So I'm going to go ahead and do compute. And these are the actual watt per meter square Kelvin HTC values that you get from fluid flow, from actual solved fluid flow. So you don't have to guess the values based on your fluid or conditions. And you can see how they are varying depending on the different locations. So it would be quite inaccurate if you were to assume just one value or one size fits all. So overall, there is a lot to gain from doing this sort of a simulation within Ansys Fluent, especially with some of the cooler features that you have available in the latest versions. And both from an accuracy point of view and from an ease of use point of view, really, this is one of the best tools that you can use to do thermal simulations. So I'm just going to go back to the presentation to cap off today's AVA. In today's session, we learned how to create interfaces for conjugate heat transfer. We learned how to set up and post-process a forced convection problem. We also learned a lot about using multi-layer shell conduction and post-processing the surfaces that are created as a result. And additionally, we learned some cool Fluent tips and tricks just to, help make the setup a bit easier. So with that, I wrap up today's AVA session. Thank you everyone for joining us today. See you next week. Bye-bye.